In this video, we will learn about stable and unstable nuclei. We'll learn about the different types of particles emitted from unstable nuclei and how to write the equations for nuclear reactions. How do we know if an atom or particle will be unstable and therefore radioactive? The answer lies in its nuclear stability. In the nucleus of an atom or ion are the positively charged protons and the neutral neutrons. Protons and neutrons together are called nucleons. We can write P superscript plus to represent a proton and N superscript 0 to represent a neutron which has zero charge. Now, although there is electrostatic repulsion between protons, another force exists in the nucleus preventing the particles in the nucleus from flying apart. This other force is called the strong nuclear force. The strong nuclear force is a very powerful attractive force acting on subatomic particles that are close together. It stabilizes the nucleus, holding the nucleons together. Because it is much stronger than the electrostatic repulsion between positively charged protons. Because the strong nuclear force acts only on particles close together, we say it is a short-range force. And it acts between protons and neutrons, neutrons and neutrons, and even between protons and protons. The more protons there are in the nucleus, the more neutrons are needed to stabilize the repulsive forces between the positively charged protons. For stability, a stable neutron-to-proton ratio is necessary. If there are not enough neutrons for the number of protons, the repulsion and attraction in the nucleus is unbalanced, and the nucleus becomes unstable. Unstable nuclei undergo decay to reach a more stable state. We can use the neutron-to-proton ratio and a special graph called the band of stability to determine whether an element atom will be radioactive and unstable or not. The band of stability is a plot of the number of neutrons in a nucleus on the y-axis versus the number of protons on the x-axis. The black line drawn at 45 degrees to the x-axis represents nuclei whose neutron-to-proton ratio is 1:1 or 1/1, and we can just simplify this to 1. The points in blue represent stable nuclei, and this blue band is called the band of stability. On this part of the band, we can see that light elements with fewer than 20 protons have stable nuclei when the neutron-to-proton ratio is about 1. In other words, the blue band closely follows the black line where the ratio of neutrons to protons is about 1:1. Elements with an atomic number or number of protons greater than 20 need more neutrons than protons to maintain a stable nucleus. In other words, the more protons there are, the more neutrons are needed for stability. And that is why most of the blue band is above the neutron-to-proton 1:1 ratio line. So for slightly heavier elements, the stable ratio of neutrons to protons gives us a value of about 1.2. For even heavier elements, the neutron-to-proton ratio is about 1.3. And for very heavy elements, the ratio of neutrons to protons is about 1.5 neutrons for every proton. Any point on the graph outside the blue band, in other words, any neutron-to-proton ratio value outside the band of stability, indicates an unstable nucleus. Such a nucleus will undergo spontaneous radioactive decay to become more stable. So how does the band of stability help us to determine which type of radioactive decay will occur for an unstable nucleus? When the neutron-to-proton ratio is to the left of the stability band, this indicates that there are too many neutrons in the nucleus. The isotope or atom will emit a beta particle. Beta particles are like high-energy electrons. Beta particles are produced from the transformation of a neutron into a proton. So the number of neutrons decreases and the number of protons increases as the beta particle is emitted. This solves the problem of too many neutrons and increases the stability of the nucleus. An example of this is when the radioactive copper-66 isotope is transformed or decays into the zinc-66 isotope and releases a beta particle. As we said, a beta particle is like a high-energy electron. Notice that the mass number has not changed because the total number of nucleons has remained the same. However, the number of protons has increased by 1, causing the transformation of copper into the element zinc. A neutron-to-proton ratio just to the right of the band of stability shows that there is instability because there are too few neutrons in the nucleus. To increase the stability, a proton can be transformed into a neutron and a positron particle is emitted. A positron is just like a beta particle, but is positively charged. This emission results in an increase in the number of neutrons and a decrease in the number of protons. An example of this is the decay of the boron-8 isotope into the beryllium-8 isotope with the release of a positron. Notice the positive charge on the positron. Again, the number of nucleons has not changed, but this time the number of protons has decreased by 1. Beryllium has 4 protons in its nucleus and boron has 5. When the neutron-to-proton ratio is below the 1:1 ratio line, this means that there are too many protons in the nucleus. What happens is electron capture occurs. An inner electron is drawn into the nucleus and reacts with a proton. The result is the formation of a neutron and the release of X-rays and gamma rays. Electron capture solves the problem of too many protons. The number of neutrons increases and the number of protons decreases. The example shows us how the nucleus of argon-37 reacts with an electron to produce chlorine-37. Again, the number of nucleons in total, or the mass number, has not changed, but stability of the nucleus has improved by the formation of a neutron and the removal of a proton. Lastly, when an element which has both too many neutrons as well as an atomic number greater than 83, in other words, a very heavy nucleus, an alpha particle will be emitted. The number of neutrons decreases and the number of protons decreases. Specifically, the number of neutrons decreases by 2 and the number of protons decreases by 2. So 4 nucleons are emitted. This results in a mass number decrease of 4, but an atomic number decrease of only 2. So an alpha particle is essentially the nucleus of a helium atom where there are 2 protons and 2 neutrons. The emission of an alpha particle helps solve the problem of a very heavy nucleus by making it almost instantly lighter by 4 nucleons. These decay processes often release energy in the form of gamma rays or X-rays. Albert Einstein's famous equation E equals mc squared, where E represents energy, m is mass, and c is the speed of light, tells us that energy can be converted to mass and mass to energy. In these nuclear decay processes, a very small amount of mass is not conserved as we would expect, because a very small mass is converted to energy at each decay. Now that we know about nuclear stability and how to use the band of stability to determine what type of decay an unstable particle could undergo, let's turn our attention in more depth to nuclear reactions. But first, what's the difference between a chemical reaction and a nuclear reaction? Thus far in your chemistry studies, you are most probably quite familiar with chemical reactions. But nuclear reactions are different. We've seen some equations of nuclear reactions a few moments ago. Let's now compare the two. Chemical reactions involve the outer electrons when two or more particles, such as atoms or ions, react. Whereas in a nuclear reaction, the nucleus of a particle is involved. In a chemical reaction, the individual reactant elements are unchanged after the reaction, although they can bond together or break apart. Whereas in a nuclear reaction, almost always an element is transformed into another or new element, or one of its isotopes. In a chemical reaction, the products are the same, even if different isotopes of the same element react. While in a nuclear reaction, different products are formed, depending on the reactant isotopes. And lastly, in chemical reactions, the energy changes are relatively small, while nuclear reactions produce large amounts of energy. Now on to the last part of this video, types of nuclear reactions. We can classify nuclear reactions into three types: fission, fusion, and transmutation. During fission, a heavy nucleus is split into two or more smaller nuclei. Energy is released, as well as other small particles. During fusion, two or more lighter nuclei combine to form a heavy nucleus or heavier nuclei. Subatomic particles are also released, as well as lots of energy. The sun and other stars generate their immense energy from fusion reactions. Fission and fusion are covered in more depth in another video. Transmutation is the transformation of an atom of an element into an atom of another element. According to this definition, fission and fusion are also sometimes referred to as transmutation reactions, although sometimes, like here, they are classified as a different type. We can split transmutation into two subtypes, radioactive decay and bombardment. In radioactive decay, an unstable isotope of an element, usually spontaneously, transforms into a new element by emitting radiation. We saw this earlier when we looked at the band of stability and the types of particles emitted by unstable nuclei. The unstable isotope is called the parent particle, and the different particle that is formed from this nuclear reaction is called the daughter particle. Many decay reactions, for example alpha decay, also give off other types of radiation, for example gamma rays. During bombardment, a target nucleus is bombarded with smaller particles, and they combine to form a different, larger nucleus. The smaller particles are usually protons, neutrons, or alpha particles. Let's clear some space and have a look at some specific examples of radioactive decay and bombardment reactions. This nuclear equation for radioactive decay is the first transmutation step in a series of decay steps of uranium-238. The unstable uranium-238 nucleus emits an alpha particle and decays into thorium-234 in the process. Thorium has 2 fewer protons than uranium, because 2 of uranium's protons were emitted in the alpha particle. And thorium has 4 less nucleons in total than uranium, because the mass number of an alpha particle is 4, meaning that 4 nucleons are contained in the alpha particle. In this nuclear equation, carbon-14 is radioactive and decays to nitrogen-14 by emitting a beta particle from the nucleus. We said that in beta decay, a neutron is transformed into a proton, and so the atomic number has increased by 1. But the mass number is still 14. The first artificial transmutation by bombardment was the bombardment of nitrogen gas with alpha particles. The fluorine-18 isotope is unstable, and so the reaction goes further with the product decomposing to give a stable isotope of oxygen and it releases a proton. Now, the transuranium elements are elements with an atomic number greater than 92, in other words, elements with more than 92 protons, and these are the elements after uranium on the periodic table. Transuranium elements are artificially made by transmutation bombardment reactions in particle accelerators. All the transuranium elements are unstable and radioactive and decay spontaneously. Now it's time to summarize everything that we have learnt. In this video, we learnt about nuclear stability and how it depends on the relative nuclear forces, those being electrostatic repulsion and the strong nuclear force. We also saw that nuclear stability depends on the ratio of neutrons to protons, and that the more protons there are means that the nucleus will need even more neutrons for stability. We looked at this graphically at a special plot called the band of stability, which shows the number of neutrons versus the number of protons in stable nuclei. The plot helped us determine stable nuclei versus unstable nuclei, and the different areas on the plot help us to determine whether unstable nuclei will undergo alpha, beta or positron emission or electron capture to improve stability. We saw what the differences are between chemical and nuclear reactions. And lastly, we looked at the types of nuclear reactions, namely fission, fusion, and transmutation, and looked at some specific equation examples of transmutation by radioactive decay and by bombardment.